So process is a random variable which is a function of time. If anything just repeats over a time, then we call it a process. A stochastic process to be exact. Because if it is not random, then we call it a process. If it is random, then we call it a stochastic process. So example of a stochastic process is number of jobs at the CPU. Right? And so you will take several observations of the jobs, number of jobs, and you know that is a random variable, and so you can find the probability distribution function for each possible t. Now this is important to understand that there are two dimensions here, and that is what we are interested in. We are interested in nt is a random variable, and we can find the probability distribution function for nt at this time, and then at some other time, at some other time. We are assuming that they have a distribution. Yeah, that's what I'm saying, yeah. Right? So we are talking about the distribution of n of t at time t. Okay? Where you take the distribution over many systems at that time. So let's take another example. Let's say people traveling on the trains. People traveling on a train, let us put it this way. Okay? There are many trains running in St. Louis right now at this time, or maybe bus would be a better example. Many buses. So I go to bus number 1 and see how many people are there, and I say 13. Go to bus number 2, there are 15 at this time, right? So that is a random number which we are going to plot at 9 o'clock in the morning, and that we get a distribution for number of people at 9 o'clock in the morning. Then I do the same thing at 10 o'clock. It will be a different distribution. Right? And I do at midnight, it will be a still different distribution. Alright, so number of people on the bus is a stochastic process, and it varies with time, and it varies with space. So an example of a stochastic process is waiting time in a queue. So waiting time in a queue will vary depending upon which realization of the queue are in and what time we are measuring. So now we have 4 different types of stochastic processes. Discrete or continuous, Markov, birth, death, and Poisson. So let me just explain one by one. Discrete or continuous is about the state, not about the time, right? So if the state is discrete, means, it's always an integer number. So number of people on the bus cannot be 4.5. It is either 4 or 5. So that's a discrete state process. Alright? On the other hand, if we had the percentage of a chemical in a solution, that would be a continuous process. That could be 4.3332%, right? So that's a continuous state. So discrete or continuous state depends upon whether the state itself, the random variable that we are measuring, is discrete or continuous. On the other hand, time could also be discrete or continuous, which we are not talking about. The time could be, continuous, which is actually it is, but sometimes you don't measure it continuously, you measure it at discrete times. You measure it at 10 o'clock, 11 o'clock, 12 o'clock. So you already made the time discrete yourself. Alright? So don't confuse a discrete time process with a discrete state process. State is about the value of these variables. And so, for example, I have drawn here nt. Actually, if you were to really draw nt, it won't be a continuous like it's shown here. It would be jumping by 1 and jumping down by 1 or going up by. So it will be more discrete state, right? So that is the thing. So discrete state means what is the value? Is it discrete or not? And discrete time is that. Anyway, if it is discrete state, we also call it a chain, stochastic chain. So number of jobs in a queue is a stochastic chain. Waiting time in a queue is continuous state. Everybody understand? Waiting time is continuous, whereas the number of jobs in this queue is discrete. Yeah. Okay, so here state means, let's say for example when we say state, we mean state of the queue. State of the queue is the number of people in the queue, could be one way of defining a state. Right? If you have a disk, there are many things that will define the state. One of the things could be number of jobs waiting for the disk. And then if you want to go further, then you have to define where the head is. That would also define the state and all that, right? So the state is something that defines the system. Yeah, when the state is discrete. Yeah, then it is called discrete state. Markov is if the process is such that all you need to know is where it is right now, and then you can tell all about the future, or you can make all the probabilistic statement about the future, that is called Markov process. In some processes, you have to know the whole life history as to where the process was born, where they studied, this and that. That is not a Markov process. A Markov process is where we say, okay, you are Bashu, so we know your current state, so we can tell you, what you end up with, 10 years from now. That is a Markov process. Understand? So, and the Markov chain is basically, if it is a discrete state process, then we call it Markov chain. So the good thing about Markov is that it makes life easier. Just like exponential distribution makes life easier because it is memory less. We don't have to worry about the previous history. Similarly, Markov makes the life easier because we don't have to worry about the previous history. In the case of Markov, all we need to know is the current state. All right. So it turns out if you have MMMQs, what is an MMMQ? Yeah, memory less, exponential arrival, inter-arrival, exponential service time, and M servers. That is MMMQ. Those can be modeled by Markov processes, as we will see in a minute. And similarly, the time spent in the queue is a Markov process, while the number of jobs is a Markov chain. Okay, chain is simply a discrete thing. So here is how you can model some of these queues is that first of all there is no person in the system, there is nothing in the queue, so system state is 0. Then at some rate the jobs arrive, and when the first job arrives you enter the state number 1. Then the second job arrives, you state number 2. Then third job arrives and so on and so forth. However, in the middle it is quite possible that some jobs may leave, they may get serviced. If they leave, then you may go back to state 0, or if you are in state 2, you may go back to 1. And so in general, if you are in state J, at some rate you will try to enter state J plus 1, and at some rate you will lose state J to J minus 1, because something will get serviced. 0, 1, 2 is arrivals. If you are going in this direction, this is arrival. Lambdas are the arrival rates. So at this rate, you are arriving, and this is the rate that we are getting serviced. So they are both arrival and service. If your arrival happens, you go to the next state. If service happens, you go back to the previous state.
But it's not the Markov chain independent, so it shouldn't be dependent on the past.
It should not be dependent upon the... Okay, so here's the thing now. This is what is happening in this one, in this case. By the way, this is basically what is happening in this case is if you are here in J state, we don't care how you got there. Okay? We know that now that you are here, you will go back or go forward. Alright? But we don't know your previous history, that you waited here 1 minute and then you waited 1 hour and then you waited 3 hours. How you got there, J, we don't need to know. But once you are in state J, then all we know is that in state J, your arrival rate is going to be lambda J and your departure rate is going to be mu J. So this is actually somewhat simplified Markov process, because in a Markov process you just don't have to go to one state or the other. You could go to third state, fourth state, fifth state. That is still Markov. So Markov process can be much more complex, but this particular special version of Markov process is called birth-death process. Why? Because only one person or one job is born or one job leaves at a time. Okay, so this is a somewhat linear or one-dimensional, Markov process, as opposed to you could have multi-dimensional Markov process. So birth death processes, you just go to n plus 1 or n minus 1. So that is basically in a single server queue, that is what happens. And if there are no bulk arrivals, if they had bulk arrivals, there won't be birth death process. Like basically you will be jumping from here to there and there. So this is very simple process. Now, Poisson processes. Before we talk about Poisson processes, let's talk about Poisson distribution. So the number of, if the inter-arrival times are exponentially distributed, then the number of arrivals is Poisson distributed. So here's the thing, you mark the arrival times of the jobs, which are marked here by these vertical lines. Those time between the job arrivals, inter-arrival times are exponentially distributed. However, if you take any time interval, let's take 1 day, in that day you count how many jobs came in, and then you go to the next day and count how many jobs came in, that's random number 2, right? The distribution of that random number is Poisson. Yeah, okay, so this is the thing, is that inter-arrival time is exponential, and when you add up inter-arrival times, exponential numbers, so that they fit your t interval that you want, that number of required for that, it doesn't have to be exponential. The number to fill in, so the thing is, you have some bubbles or something that are exponentially sized, right? And you put them into a bucket. So how many will fit into that bucket? That cannot be exponential. So if you derive the distribution, whatever expression you get, that is called Poisson distribution. So the inter-arrival time is exponential, the number of arrivals is Poisson. So when you have so both of these are, so basically, and here is the formula. When you have exponential distribution, you write down f tau is equal to lambda times e raised to minus lambda tau. Expected value is 1 upon lambda. So that is the distribution, exponential distribution. For Poisson arrival, the probability of n arrival in time t is lambda t raised to n e raised to minus lambda upon factorial n, and the expected value is lambda t. So, basically they are both same because your expected arrival is 1 upon lambda per second, 1 upon lambda jobs per second, and here the expected number of arrivals in t seconds is basically that t upon 1 upon lambda, which is lambda t. So this gives you that you will get these many jobs. So whether you say memoryless or you say Poisson, that is the same thing. Whether you say inter-exponential or you say Poisson, they are all the same thing. So we use 3 different names. We call them exponentially distributed inter-arrival times. We call them memoryless arrivals, and we call them Poisson arrivals. Exactly, but the name of the process is the same process, and we can call it any one of those 3 things. Alright, so reason we call it memoryless because we don't need to know the history. Reason we call it exponential because the inter-arrival time is exponentially distributed, and reason we call it Poisson because the number of jobs in a particular time or any interval is Poisson. So the property of the Poisson processes are, and they are very common in queuing theory, and the property of the Poisson processes are that if you take any number of Poisson processes and then add them together, you get a Poisson. They are additive. So you take lambda 1 arrival, lambda 2 arrival, lambda k arrival, so these are the rates, lambda 1 is the rate, lambda 2, lambda k, and you merge them together. The total arrival will also be Poisson with arrival rate lambda is equal to sigma of lambda i's. If you split a Poisson arrival probabilistically, so that with probability P1 you send them this way, with probability P2 you send them this way, with probability Pk you send them that way, then each of those sub-streams is also Poisson. And if you have a Poisson arrival and you service it with exponential service time, then the departure is also Poisson. So if your arrival is memoryless and your service is memoryless, the departures are memoryless. That's what it is. If you have you split it before you serve, right? Like this, you have m servers, but they are memoryless servers. So when you split it and then the departures come out, they are still Poisson. So not only the departures from MM1Q are Poisson, MMMQs are Poisson, the departures. Alright. That brings us to something that is not in the book but has become very popular in the recent days. It will be in the next edition of the book, called pasta properties. Before I go to pasta, let me just summarize the Poisson process. Poisson processes are good because you can combine them, still remain Poisson. You can split them, they still remain Poisson. You can go through the MM1Q, they still remain Poisson. You can go through MMMQ, they still remain Poisson, right? So those are the four things we talked about. Now, pasta property. Pasta property is that the Poisson arrival C time averages. PASTA. Since it is not in the book, please listen carefully, okay? This is the only write-up you will see, unless you can go to some other place and check them out. Okay, so random. So basically, Poisson arrivals are random arrivals from a large number of independent sources. The reason we see Poisson arrivals in practice, and we can justify Poisson arrivals, is because if you have something, just like why we justify normal distribution for the errors, is because when you have something from large number of sources, and the arrivals from large number of sources, the times automatically become exponential and the process automatically becomes Poisson. Okay? So Poisson arrivals are random arrivals from a large number of independent sources. So if an external observation samples a system at random instant, what they will see. So let's see, suppose there is a system, a Q system, in which and it is a DD1Q. DD1Q means deterministic departures, deterministic arrivals. So suppose the arrivals are 1 jobs per second and the service is 2 jobs per second. So one job comes in here, but it is served in half a second and goes away. Then the second job comes in after 1 second, it is served for half a second and goes away, and so on and so forth. Right? Now, if somebody monitors this and happens to see only at every second, what they will see? They will see either 0 or 1. If they just come before the customer arrival, they will see the queue is empty. If they come just after customer arrival, they will see the queue is busy. Right? But they are not really seeing the exact thing, which is the queue is busy only 50% of the time. They won't figure that out. Right? On the other hand, if you had Poisson observation means you randomly come and just check it. Right? Then sometimes you will see it busy, sometimes you will see empty, and then you will see exact time average of the process. Now the important property, pasta property, is that if you had some other distribution of your sampling, you will not get this property. Only Poisson sampling gets you this property. Obviously, deterministic sampling doesn't give you that. And so whenever a lot of people do sampling, sensor networks or anything like that, they sense something, they might just put it every second. Alright? Clearly, on a deterministic process, they're not going to get the right thing. Right? On the random process, they may not get the time average either. So your sampling, your sensing has to be Poisson to get the time average. People who have not taken the course, they don't know all this, and they just go ahead and measure it, and then they publish it, and then they come out happy, but not really representing the real world. So pasta property simply says that the Poisson arrivals see time averages. And it's the Poisson sampling that you have to do. Whenever you want to sample or sense a system, you have to do Poisson sampling. Alright, that brings us to the summary of this whole chapter, or actually not of this whole section which is on the processes. That Poisson processes are one where the arrivals are memory less, and then the birth-death processes are the one where you just go to the next one, and the Markov processes are the one where you just have to know the current state. So all birth-death processes are Markov, but not all Markovs are birth-death. Similarly, all birth-death processes are Poisson, but not all Poisson processes. All Poisson processes are birth-death, but not all birth-death are Poisson. All right. So here's a quiz just to make sure that you understood. And so please go ahead and do it in 1 minute. All right. Let's go to the solution. First of all, birth-death processes cannot have bulk service. Because if they have bulk service, they will not go to the next state. They will go to 5 states before or something like that. So that is false. Merger of Poisson process results in a Poisson process. That should be kind of trivial. The number of jobs in a queue is a Markov chain. Okay? Because Markov was already given, all we wanted to figure out whether you understood the chain. And here is a discrete time process is also called a chain. That is false. Why? State. We are looking at the state, not at the time. Alright, that brings us to the end of this chapter. First we learned the Kendall notation. So now we understand what is MM1, MM2, MMNK, MMKQs. And that we know that we have to measure or quantify number in the system, number in the queue, number in waiting, number in service rate, etc. might be given. Then we know the Little's law. Now Little's law have to be remembered in some sense, because this is not something that will be given. Basically this is something that we remember in our brain, and the formula is n is equal to lambda r. N is the number in the system, lambda is the arrival rate, and r is the time, response time, or time in the system. N is equal to lambda r. And then we saw the processes that are Markov, birth-death, or Poisson. Poisson means IID and exponential derivals. Birth-death means adjacent states. And Markov means only current state is required for future evolution.